Hello, and welcome to a tutorial on parametric analysis and optimization in ANSYS Workbench. In this tutorial, we will first generate the geometry and then do the parametric analysis and optimization. So to begin with, under Component Systems, I will click on Geometry, drag and drop. I can see that it's ready to move on. My geometry is up, so I'll double click on geometry. Now space claim is starting. Once space claim is started, I'll go ahead and close this window. And I like to work in the XY plane, so the first thing I do is right click, select new sketch plane, and come over and select a point in the XY axis and click OK. I click on Plan View, and now I'm looking at my diagram straight on. If I wanted to change any options, such as my units, I would go to File, Units, and click on Units here, click on meters for example, and then go down and change my spacing. I'll go ahead and leave it as millimeters. First thing I'm going to do is build my geometry by starting with the wall. So I will click and generate my wall. That'll be 20 millimeters by 20 millimeters. I can then pull this, and I'm going to pull this geometry back 10 millimeters. And go ahead and look at my geometry face on again. Now I'm going to create my circles, but I need to go back to my sketch plane, so I click this top there. Now I click on my circles, and you can see that right here with the cursor the way I have it, I will not be able to draw a circle. I need to have the pluses checked. So I click once, now I have my plus, and I can go ahead and generate my circle. I'll make these circles 4 millimeters in diameter. I will now make my second cylinder by clicking on Move. Click this circle, click along the vertical axis, hold down the Control key and slide the circle down such that it copies that circle, and I will make that so that they are 14 millimeters apart. I now have my two circles. Now I'm going to go ahead and extrude those, or pull them. So I'll click on Pull and Control click on the bottom one, and I'll slide those out. And if you can see, I'm not getting any cylinder to show up. So I actually need to undo this command and click on the Add. Now when I pull these, you can see that material is being added to the geometry. And I'm going to go ahead and make these cylinders 30 millimeters long. Now I'm ready to go ahead and add the end to this. My end is going to simply be a rectangle, and so I'll go ahead and go back to my sketching view. I'll look at this straight on in the Z direction. I'll create a rectangle, and I want this to be right around the body of the cylinders. So I make my geometry there. Now I'm ready to pull that, so I'll rotate, come to the Pull command, click Pull, and slide that out. And that won't work because I want to pull out these cylinders as well. So I'll hit the Undo command, click the top cylinder, Control click the middle face, and Control click the bottom cylinder. Now when I pull this, I will get my whole geometry. I just got the face there, so I'll go ahead and undo that, and now click and pull, and I will make this 5 millimeters long. Now there's a face hidden here, and you can see if I come back to the structure tree, I have that surface, and I won't need that surface, so I'll go ahead and click on it, right click, and then click delete. I now have my geometry. and I'm ready to go ahead and add the parametric parameters that I want in my analysis. To do this, I come to the cylinder and I click on the cylinder, and as you can see, I now have this 2 millimeter radius with a P showing up. A P stands for parametric. When I click on that P and come to groups, I can see that I have created a group 1 that's based on the radius of that first cylinder. You can now see the P has been grayed out, meaning you've already selected it to be a parameter. So I'll come to group and I will click on group and click on the 2 millimeters if I wanted to change it, or I can double click group and rename this top radius and then hit enter. I'm now ready to come down to my bottom cylinder and click on the line, and you can see that I can now click on the P again. Group 1 is started. I'll double click on that and double click on group, and I will type in bottom radius. Those will be the only two parameters that I'm going to set: the radius of these two cylinders, which will also affect the radius of this end surface as well. So I have now created my geometry, and I'm ready to go ahead and bring this into ANSYS Mechanical. So I will minimize this, and you can see now that when I created those parameters, I now have this part of my project schematic screen that's showing my parameters. And if I double click on the parameter set, I can see that I have a input parameter geometry. P1 is my top radius. The current value is 2 millimeters. I also have a P2, which is my bottom radius, and 2 millimeters. I have not selected any output parameters, as those will be selected in ANSYS Mechanical. So I can go ahead and close this. Now I will go back up to a static structural. So I'll click on static structural. I can drag that to the geometry and let go, and this will automatically link my geometry to my static structural. Now I'm ready to open ANSYS Mechanical, so I double click on model. To save time, in the remaining part of the video, I'm going to use analysis that I've already performed and just walk you through the steps. So after opening Mechanical, I'm going to click on the geometry, and I can see that I have my one solid that has been brought in, and that all looks good. I can pass on coordinate systems. I've already meshed this, and I simply did a generic default mesh with a size setting of fine, and you can see that down here. If I click on sizing, I clicked the drop down here and selected fine and generated the mesh. You can see that I have some named selections that came in, and this is my top diameter and bottom diameter, which were created in my geometry development. So I can now close that. In static structural, you can see that I've added a fixed support, and on the fixed support I added the sides of my pretend wall. I added a force, and the force I added was on the end of the bracket in the vertical Y direction, pushing down. The analysis that I performed was an equivalent stress and a total deformation. Now, in order to use the values that I want as outputs in my parametric analysis, I need to come to the equivalent stress and come down to the details of equivalent stress and scroll down to the magnitude and click on maximum, so that I get a P, and that P there will represent or imply that this maximum equivalent stress is now being considered as a parametric value. I also need to come up to the geometry, and on the details of the geometry I want to use the mass as a parameter. So I will come down and look at the properties and click on mass such that it also has a parametric value or reading and will be considered as a parametric parameter. So now that I've created and performed that analysis, I'm ready to close the ANSYS Mechanical, and this is the project schematic screen that will show up when you're all done. I'll go ahead and explain these components as we go through the rest of this tutorial. To explain a little bit more about the project schematic screen before moving on to the parametric analysis, you can see now, after I have done this analysis under my model and solve my model, I get these arrows that loop around showing that there are inputs and outputs to my parametric analysis. The outputs will be the stress and the mass. The inputs will be those two radius values of the cylinders. You can see that there are only inputs here. You can see my geometry is connected to my geometry. And now if I want to double click on my project set, it'll bring up this window and it'll show me that I have input parameter of top radius again, and the radius here is 0.1. Before it was showing you the diameter, which was 2 millimeters. Here's my P3, which is my bottom radius of 0.1, my geometry mass, and my equivalent stress. And these values came from the analysis that I did on my default values. Down here I have not had to make any changes to anything in the properties of the parametric set. Now over here what you can do is you can go ahead and right click on this DP21 for example and click copy inputs to current, or any of these other things you can click on. One that's commonly done and that I've done here a bunch of times is duplicated design point, and what that does now is it lets you go in and change the values on these design points and rerun an iteration, and that lets you do a what if type of optimization or parametric analysis, where you can come and change the values of the top radius, the bottom radius, and then it will compute the mass and the maximum equivalent stress. And you can enter in any values that you think you would want here in any range, and instead of having to go back and do that in your geometry, update your geometry and all of that in both the geometry modeling and ANSYS Mechanical, you can do it all right here. So that's a handy feature, and that again is all done just by using parameter set and double clicking on that. The next thing you will want to do is scroll down to where it says Design Exploration, and when you do a parametric analysis, the first thing that you want to do is to determine the correlation between the parameters that you're looking at. So in this particular case, I want to see how the two radii interact with each other. After doing that, we will generate what we call the response surface. And the response surface is a mathematical model of the correlation between my parameters. And then my final step will be to come down and do a response surface optimization. So I'll do an optimization based on the mathematical surface that I attained in this step. This parameter correlation is brought into the model simply by clicking on it and dragging it, and it'll bring up this C drop down or work tab here. When I do my response surface, it will bring up D, which says response surface, and then my final one will be response surface optimization here in E. And you can see that the response surface and the surface optimization are connected. So we essentially take the design of experiments performed in the response surface over to the optimization, and also the response surface over to the optimization. So to go through each one of these steps and explain a little bit about them, I will go ahead and double click on parameter correlation. And again, this one's fairly straightforward. You can see that we have our two input parameters, our output parameters, and you won't need to change anything down in this window. The defaults will be okay for most analysis that you will do. When I click on the parameters correlation, you can see here the input parameters and the output. You can see the R2 contribution. You can see a correlation value. You can see that these values are 0.79 and 0.73, and those can be high or low depending upon how you look at it. We can look at the input parameters, output parameters. If I click on these, I can just turn them on or off. When I scroll down now to look at the output, the first thing I can do is look at the design points. And here I selected to do 30 design points, and that was done up here in the parameter correlation. So under this first tab, I scrolled down to size of generated sample set was 30, and maximum number of major inputs was 2, and the rest of these are default values. You'll often want to change the correlation type, but other than that, these parameters can pretty well be left alone. The default down here on size of generated sample set is 100, so unless you want to spend a lot of computation time, you'll need to reduce that number each time. So you can see the design results, or excuse me, the design points that I selected actually were selected by the program. My bottom radius here was given a 0.10419 and a 0.056, and it computed the mass and stress based on these two design points. And it's done that for all 30 inputs, or all 30 design points. I can come to my charts and look at a correlation matrix. This correlation matrix is helpful. The red indicates that there is a very strong correlation, a correlation value of 1. Dark blue means there's also a very strong correlation, but it's an inverse correlation. So if you look at this plot, dropping down along this vertical axis, we have our bottom radius, top radius, which are our two inputs, and then our two outputs. Going across the top here, we have our two inputs and our two outputs. So this shows that there's a very strong correlation between the bottom radius and the bottom radius, which makes sense. And so all along this diagonal, you'll get bright red indication that says that you've got a very strong correlation. This is also interesting to show that down here I have blue, and in my equivalent stress maximum and my bottom radius, there is a pretty strong correlation between my equivalent stress and my top radius. There's also a strong correlation. And then I obviously get these dark blues when I go to compare my outputs. So this table here can be can be very informative. It can tell you that you may not need to consider some particular correlations. If you have correlations that are down here in the light blue, gray, and light yellow, you may omit those from the rest of your analysis to reduce the computation time. You can also look at the sensitivities. You can see here my sensitivities are about equal. You can look at a determination histogram, determination matrix. This is similar to what we just looked at, and then a correlation scatter. And you can see here that my data is relatively linear for the data points that I have used. And when you have this all set up and want to perform the parametric correlation, you simply come here and click update. And when you click update, it can take a long time depending upon how many inputs and outputs you have, as well as how many design points you have selected. So that's the parametric or parameters correlation box. After that has been done, you can come over to response surface and do your design of experiments. So double clicking on the design of experiments, a similar window pops up. You can click on design of experiments and change any defaults that you want. The design of experiments type can often be changed, and there are several options. The default is central composite design, but that can take some time. An optimal space filling is often good, and this Latin hypercube is also a commonly used design of experiments technique. In this case, I simply used central composite design. You can come down and look at the output now after you have clicked update and look at your results. Here's a sketch showing the relationship between the parameters. This is actually very hard to see much correlation and what's going on here. If we look at the design points versus parameters, here I have my geometry mass and the design point that I'm looking at, and you can see how the mass moves up and down according to the data that you used. It was auto-defined by the program. So now we can look at the response surface, and this is generated based off the design of experiments data. Again, you can look at the defaults. Everything here is okay. You can see your inputs and your outputs. You can do a min-max search, and you can see the maximum values obtained from your geometry, both in equivalent stress and mass. You can come down here and look at goodness of fit. You can look at verification, all types of outputs that can be considered and looked at to determine how good your design of experiments was and how good your results are up to date. After looking at and reviewing this, we now bring up our response surface optimization. This design of experiments and response surface are already added. They will be default. They will default and bring these values in. Then I can click on my optimization, and this essentially presents your results. This can take some time to run. When I click on my optimization, I have several things to set down here. The number of initial samples, the number of samples per iteration, and the maximum allowable Pareto percentage are important values to look at. This is default to 70. This number of initial samples is often default at 100 and then 50. I have reduced those down to reduce the computation time. In terms of results, you can look at the convergence of the P3, which is one of my values, and you can see how it bounces around and then converges down here to just under 0.9. I can look at my other value and see where it converges down here to around 0.07. My minimize of my mass minimizes down here, and this is where you also set up your objectives and constraints. So here you can see that I've taken my bottom radius and I have said minimize that bottom radius, and my top radius I have said minimize. My geometry mass I have said minimize, but on my equivalent stress I have selected to seek a target stress of 1.5 e to the 5 pascals, and I've come over here and set the drop down to be less than that, and the upper bound is 1.5 e to the 5 pascals. So now when I come down and look at my results, you can see that my bottom radius is 0.0875, 0% change. My top radius is 0.07 with a reduction of 0.06. My parameter value here for my mass is 2,067.3, which is a reduction, and you can see that the value for the stress is 1.497, which is really close to the 1.5, but there is a slight increase from the default before. You can see that there are 3 candidate sets here, and that's because back up here in the optimization I selected that the maximum number of candidate sets that I wanted was 3. If you wanted more, you need to change that value. So I can look at my candidate points, and this is where you essentially get most of your information on your optimization analysis. This gives you 3 candidate sets that will work based on the parameters that you gave your optimization. You can see trade-offs and see how these values trade off relative to each other. You can look at the samples you considered, and you can look at the sensitivities. So now I can close that, and I hope this tutorial has given you a little bit of an overview of how to do a optimization and a parametric analysis in ANSYS Workbench. Thanks for watching.